Okay, good morning everyone. Thanks for coming. I'm Mike Leach, I'm an engineer with ARM. I work for the Development Solutions Group, basically on debug tools. What I'm going to give a brief talk about today is the open source CoreSight Trace decoder that we're developing jointly with Linaro and TI. So, as I mentioned, the project is a joint project between Linaro, TI and ARM, and what we really want to do is create a reference open source trace decoder for all ARM CoreSight systems. So this includes all the Cortex profile cores, A, R and M, and will include non-core trace elements such as ITM, STM, bus trace, and anything that comes along in the future, basically. So the architectures just covered are both the 64-bit V8 and the V7 architectures. The intention is for the library to be usable with a wide range of tools. That's both on-target tools such as perf and off-target tools, so for offline analysis. It's implemented in C++ with a C API wrapper available, and it's currently available. The first code is up on GitHub, so you're welcome to have a look and let us know what you think. So this is a quick reminder of what CoreSight Trace looks like. You have a number of Cortex cores. Each has an ETM, or in this case I'm using ETM to mean either ETM v3 or 4, and could be a PTM. At some point, some program will program up the CoreSight components. Each will have a unique ID, unique trace ID, represented here by the colours. All the information from each core as it's tracing will go through a CoreSight funnel and into some sort of capture buffer. So the capture buffer, the information in the capture buffer, which is all the trace mixed up, is what we're interested in. And at some point, the trace will stop and will be ready for decode. And this is where the library comes in. So the principal API in the OpenCSD is what we're calling a decode tree. This represents the hardware. As we saw earlier, if you look, the diagram on the left shows that we have a demultiplexer, which takes the raw trace input and sends it to packet processors and packet decoders for each ID. Now, for each trace ID, you have to configure the decoder according to how the original hardware was programmed. So this configuration will vary according to the type of ETM or PTM used. So the API has functions to allow you to build up a tree of decoders according to your specific use. So there's no requirement to decode every single trace source if you're not actually interested in that source. Finally, we also need, if you're doing the full trace decode, you need to give some access to the original opcodes. That's through a program memory accessor on the left. And the operation of the library is a simple pipeline. We push the trace data from the top of the decoder, and what we get out is what we're calling generic trace elements. These will typically be instructions executed or processor states. What we have here is a bit more detail on the trace data path. So the trace data goes on the diagram on the right-hand side. You can see the trace data goes through each of the components: the trace deformatter, packet processor. The packet processor takes raw data and turns it into discrete packets. The discrete packets then go to the packet decoder. where they're transformed into instructions executed, etc. And the output is generic trace elements. The key here is that all ETM architecture-specific information will have been removed at this point, so the analysis program can then take the trace elements and do whatever it wishes to do with them. That may be provide disassembly for the trace. It may be simply to look at the addresses traced to run code coverage or other such analysis. So there's a feedback path from the output, which allows the analysis program to either say continue, we want more trace, wait, I've got enough for now, or there may be fatal errors that need to be signalled along that path, at which point the decode will have to stop. So the input path is a single input API function which has 4 possible operational codes that we use. The data one is simply telling it we're putting data through there. And we have a code to allow the input to signal this is the end of the trace, we're at the end of the buffer. Because the analysis program can tell us to wait, we're not ready for more decode, then we need an operation to restart the decoder and flush any additional information before we start putting more trace through it. And finally, there's an option to reset the decoder completely. So if you built up a decode tree that you want to reuse, you may want to put this similar sorts of data through, or have different data blocks that you want to decode, then you can reset the decoder and start the decode process again. The analysis program and the components within the data path can provide the feedback, as we've mentioned. The response code are grouped into continue, that's fine, we can do more data. Wait, which is, as I mentioned, we need to stop processing for now. And there are some fatal codes, where the process may have actually hit an unrecognized code, or there may be other problems with the program. So these are referred to as groups because obviously in terms of fatal, we've got a number of possible fatal codes that will stop the decode process. So finally, the output point. Any analysis program will register a callback to receive the output elements. And the elements describe the instructions executed, core state, possibly timestamps, data operations if we've got data trace, and other possible trace events. There's a small example there on the left where we can see we have a stream of elements which describes what's going on in this trace. We see the trace switches on. We get the context for the core, which tells you it's non-secure 64-bit. And then we get a series of instruction ranges. These just represent a number of instructions that have executed. We may get exceptions. Another possible output is the not accessible. This simply means that we don't have access to the memory for that particular trace area. So the decoder will have to stop outputting decode information until we trace into an area that's got we have valid memory for. So a brief update on the current status. Certainly the major library infrastructure and some of the test harness is complete. We are in a position now where we can take trace data and push it through the system. I'm currently working on the ETM v4 decode, and that's approaching a position where we're going to be able to try and decode real trace with it. As mentioned, the test harness allows decoding of trace snapshots. The snapshots format is a description in terms of text files of the decode hardware, key values of ETM registers, plus the actual trace data and any memory dumps that are required for decode. What we need next is, we certainly need to do some more testing for the ETM v4. We'll be looking to build ETM v3 instruction trace and PTM instruction trace. Data trace will follow probably a little further down the line. Okay, well, that's pretty much a brief outline of the architecture. Quite happy to answer any questions you may have now.
Question, implementation-wise, what dependency actually that library has, current and possibly future one? So kind of what other library you depend on? So is it standalone C++ library, or it has dependency on, I don't know, libxml, whatever?
No, it's completely standalone at present. I don't envisage there being any other dependencies beyond the just standard C++, just the standard libraries. Yeah, it is effectively standalone. It can be built for both Linux and Windows, and should you want to do offline analysis in a Windows tool. So it's designed to be multi-platform, and obviously we'll build on our own platform as well.
So, and what use cases actually do you see for this library? So one is sort of obvious. So you have we have like sysfs or procfs actually interface to collect actually the traces, right? Matthew was working on, and you can go and actually run through the actually decode. But what about the rest of the tools, like integration with GDB? Probably actually another one, right?
Yeah, Matthew is currently looking to integrate perf, Linux perf, with the well, we're looking at integrating this library into Linux perf. So Matthew has been working on the side of perf that will set up all the trace hardware and capture a data file, and we're going to look at how best we use the decode library to create a perf report, so that you get the simplest thing that you can currently get with Intel, in that they provide a trace report in that respect. We do have customers who are interested in doing post-crash trace dumps, where they set up their trace system to be continually tracing. So you've got an ETB which will wrap around, and when they see an exception, they have the trace system set up to immediately stop capture, so they can then take the trace dump and decode on the fly to determine what went wrong. So in some in an active system, and remove the process that was causing the problem, or do what action they consider correct. I mean, the main goal of the libraries is to simply decode the trace. It's up to the analysis application to decide what he wants to do with it.
So this sort of crash analysis, or even like kind of breakpoint kind of analysis, if it would be actually integrated with GDB, that would be a very useful actually use case. So in some sense, if from GDB you can go and actually tell, okay, I want actually this particular actually user land to enable instruction tracing, right? And kernel will enable and disable it actually only when this actual process actually runs. And then when you hit actually any particular breakpoint, or actually if you crash, you can ask actually GDB actually, okay, now actually go actually pick up actually those actually traces and display actually all those instructions actually backwards. So it would be very invaluable in the cases where you, for example, like you corrupt the stack, right? You wipe out actually your addresses and there is no backtrace whatsoever, and you can go like saying, okay, in fact, actually in this case, you probably can even like consider to go integrate yourself with GDB. There is actually GDB actually reverse sort of like kind of like reverse execution actually engine, and currently it's based on sort of like single stepping one. So in this case, you probably can retrieve all those buffers and hook up actually to the same engine actually, and then in some sense actually you can even like set breakpoint backwards, similar stuff that you have actually in the DS5 or whatever. Like you just say in GDB actually run backwards and it just kind of hit breakpoint, and you can sort of like step forward. That would be actually pretty cool in terms of kind of usability of this actually.
The GDB As far as I know, we are just doing perf for the time being. GDB is an obvious case, especially that the Intel PT is integrated with GDB already. And there is a guy, Yao Li, who is working in Cambridge, but he's a Linaro assignee, he's GDB maintainer. So I'll have to pick it up with him pretty much, because if it happens, it's going to be him doing this. I don't know whether Yao is here or not.
Well, I brought it up actually when they discussed GDB actually. So.
Yeah, just on the dumping trace on a crash. I've seen some patches from Intel to enable something similar for the kernel with Intel PT. So it'd be cool if anyone who's working on this could maybe review those and make sure that they don't design something that doesn't work well with this, because they essentially set up the Intel PT into a ring buffer and then do exactly like you say. When the kernel crashes, they pass that off via K crash dump, I think. And then they K exec a new kernel, which dumps the trace, leading up to the kernel panic. And it looks like a really, really useful feature.
And just developing on the kind of GDB integration, if in fact actually if you can go and include the trace in the core file. So for example, like you go actually say through the procfs speed interface, you can say, okay, enable the actual guy, like ring buffer actually tracing. Then actually the guy actually runs, kind of crashes. Core file is supposed to be actually kind of created, so you can go and actually put all your traces associated with this guy actually in some ELF nodes, right, or whatever, like core file, actually ELF file. And then again, you can teach GDB actually go actually to pick it up, and again, actually it would be actually quite actually cool. Other tool that I had in mind actually, which is a bit I'm kind of a bit disappointed actually in terms in that you choose actually C++ actually as implementation language is actually SystemTab. And SystemTop, actually, that's the guy who is run in the kernel, right? And in some sense, actually, you can go and think about similar integration with SystemTop, where you specify breakpoint, right? And then you can also, through the SystemTop, you can go collect actually the traces. And in the SystemTop language, theoretically, you would want to go and actually say, okay, now actually, I'm actually this actually event and this breakpoint, go actually decode this thing. But that means actually your library actually kind of should run as kind of system, as everything in SystemTop kernel module run actually as inside of the kernel. So I'm not sure, is it C++ running inside of the kernel? Is it like challenge or it's, if it would be like just C library with me.
It's technically doable, obviously it won't be merged, but it's technically doable. Yeah, there were modules, out of 3 modules written in C++. So if you wanted to do SystemTab, is doing it. So I was saying that there were out of 3 modules written in C++. Technically, it just works. There's not a big deal. SystemTab is doing their own stuff anyway, so if someone wanted to integrate with SystemTab, it's doable, I guess.
It will be problematic, right? If it would be C, it would be much simpler, actually.
Well,
right?
it's C++.
All right. That's what I have.
So I think also there's, worth to bear in mind that there are a couple of components here that are separate. One is kind of the configuration, how to set up the trace and how to generate and trigger it and get it, written out. And some of that work is being done by Matthew right now. There is the trace decoder, which is a separate library, which Mike's been doing. That is just once you have the trace, how do you decode it? How do you get the data out of it? And that's the problem that the decoder handles. And so the other use cases will utilize that library to get actual actionable data out from the traces that have been captured using other means. So there's all these use cases that, and I think there are some very good proposals here that will have to be set up separately, either whether it's within the kernel, whether it's post-capture analysis, that will incorporate the decoder to actually get information that you will have. The trigger of the trace isn't part of the decoder, but is part of everything else, and that's where the whole ecosystem and the community comes in as well.
I think it's well understood, the model. Actually, I'm just like saying that the SystemTop, the use case, you define breakpoint, right? And then, yes, you interface with the starting collection actually somehow. That's actually easy because it's already in the kernel. And we've talked about like you have currently actually SysFS interface for it, right? So, but we've talked maybe actually you can kind of go and create official APIs that SystemTop can go and actually use, enable actually the stuff. But once you hit actually this actual breakpoint, let's say I want kind of very simple one, print whatever, like 100 last instructions before actually I get actually to this one, right? And that would require actually decoding library. But by nature, kind of the way how the SystemTop is implemented, it's actually all these actual logics that would actually do actually this print is kernel. So it's a kernel module. So that's become, so it makes it more challenging in some sense. Actually, SystemTop probably you can come up, SystemTop capture this buffer and store it somewhere actually in the file. So you later do actually the decoding, but it's becomes quite cumbersome and not maybe very convenient. So.
Other questions from other people?
So one of the problems that we're having is that our trace format is slightly different because of bugs in hardware, because we have our own ETM. Is there a way to like signify like at the beginning of the file and then have the library do the post-processing correctly? We'll be adding obviously the workaround inside the decoding, but I was just trying to figure out, is this acceptable to put into the library as of right now?
With that, in order to do the decoding, so the markers are already there. In order to do that integration, you'd have to start with a tracer. So you'd have to come up with not only a CoreSight driver for your own IP, but also a PMU that wraps around it so that perf can interact with it. So that's the first thing. Part of the perf interface is the transfer of metadata from kernel space to user space. Right. And in there would be the markers, the keys that would allow the decoding library to get into this funky mode that, makes your traces decodable with some enhancement from your side. Right. Okay. So it's all about it's all about the decoding library, understanding what kind of tracers it dealt with for this trace. Okay. Just more.
So, question actually kind of for this library in terms of like description of actually all possible actually events. Do you have like external metadata that describe them, or are they actually hard-coded inside of the library? So if I have custom kind of like events, right, or actually vendor has actually its own actual events, how actually they would be integrated actually into the library? Do I need to go and actually add actually kind of new, I don't know, data structures and tables actually into the library itself, or they can be actually specified as separate, I don't know, like some files actually that the library reads and understand actually what format of those messages? Yeah,
it would be expected that if you have a complete proprietary type of trace, that you'd have to write a decoder, effectively write a decoder that as part of the library itself. The existing decoders will decode just the specified ETM-v4, ETM-v3 trace. So if you had something that was not one of those, then you'd use the library infrastructure and implement your own decoder. Will be one possible route. A second route would be to write something that's outside of the library that converts your format into something recognizable by the library. Either approach would work. But there wouldn't be anything, it's not data-driven per se. To get the efficiency, it is very much a specific decoder will only actually decode one trace protocol. So which is why we're talking about having multiple protocol decode is within the library. Okay, if there's no more questions, thank you very much.